Good morning, students. Yesterday, one simple point while explaining about melting and boiling point, simple sign variation, symbol variation is there. Explanation is correct, but on a simple correction about melting and boiling points. In last class about boiling point of 15th group elements given like nitrogen is less than, phosphorus is less than, arsenic is less than, Sb is less than Bi. Given like. While explaining just due to the inert pair effect, your explanation given clear information, but side is according to the experimental analysis due to their bond strength, your metallic bond strength, not between element and element strength, between metallic strength, metal and electrons strength is present. That is the metallic bond. That's why slight variation instead of this, better you take as like this. One is. Then melting point also given like MP is equals to given nitrogen is less than, phosphorus is less than, arsenic is less than Sb given. Then again here grade less than given like this, Bi given this is. Here also same explanation. Here thing is instead of this less than, take a greater than. This is a small correction. Everything is okay. Now today, after these variable oxidation states, yesterday explained in chemical properties of 15th group elements. Next important concept is anomalous properties of nitrogen. Very, very important concept this is. Anomalous properties of nitrogen. Here 15th group elements 5, nitrogen, phosphorus, arsenic, antimony and bismuth. Among these 5 elements, nitrogen shows some peculiar properties. Nitrogen, phosphorus, arsenic, antimony and bismuth. These 4 elements, some properties, and this 1 element property, somewhat in some properties differs. That's why anomalous properties of nitrogen regularly they'll ask for 2 marks. Anomalous properties of nitrogen or oxygen or fluorine like. Here, nitrogen shows some anomalous properties with the same family members is due to main reason is due to its small size. First reason. Due to its small size, its electronegativity is more. That's why high electronegativity and ionization energy. Then third one is unavailability of d orbitals in its outermost orbit. In its outermost orbit. So these are the reasons, 2 to 3 important reasons to show the anomalous properties of nitrogen. So here small size means here the top to bottom nitrogen to phosphorus, arsenic, antimony and bismuth. Top to bottom size increases. That's why small in size. When our small in size, high electronegativity and high ionization energy. And while writing its electronic configuration, nitrogen electronic configuration 1s2, 2s2, 2p3, there is no 2d orbitals. That's why absence of this orbital, electrons cannot excite. That's why they show some important peculiar properties, anomalous properties of nitrogen. Sir, how it shows anomalous properties means generally nitrogen forms with the same element at triple bond, nitrogen triple bond, or it forms the almost all same size and same electronegativity, carbon and nitrogen are triple bonds, and they are the nitrogen and oxygen double bond is formed. In all the three cases, nitrogen pi bonds are there here. Here also two pi bonds are there. Here one pi bond is there, one sigma. All the pi bonds in all the three cases, pi bond is only one atom of p orbital and another atom of p orbital. Sideways overlapping takes place, it forms a pi covalent bond. Sideways overlapping, end-to-end overlapping we know. Here nitrogen atomic number we know. Here 5 valency electrons in its outermost orbit. 3 are the unpaired and 1 is lone pair. So Lewis dot structure for nitrogen we know. This is the 2s, one lone pair is there. It is the 2px, 2py and 2py. 3 p orbitals are present. This is the, for example, maybe 2px. This is the 2py. Maybe this is the 2pz. And electrons some are present in s orbital too. And another nitrogen atom also same thing. 2 lone pairs are present. And this is maybe 2px, this is the 2py, and this is the 2pz. This is the 2pz. So take as it is originally it is 2px, 2py, and 2pz. It also it is 2px, 2py, and 2pz. In chemical bonding, overlapping, SS overlapping, SP overlapping, PP overlappings are there. One nitrogen atom 2px, another nitrogen atom 2px, end-to-end overlapping takes place like this is 2px and 2px, end-to-end overlapping takes place. It forms a nitrogen single bond, sigma covalent bond. After formation of a sigma covalent bond, remaining bonds are the multiple bonds are the pi covalent bonds. That's why this is the 2py of one nitrogen atom and 2py of another nitrogen atom. This is the p orbital and p orbital. Sideways overlapping takes place either above or below the plane of the axis, like internuclear axis. It forms one pi bond. That bond is formed by p orbital of one nitrogen atom, p orbital of another nitrogen atom. That's why it is called a p pi bond. And here this is the 2pz and 2pz. This is only for understanding purpose. Dots and design only for understanding purpose are these dots. 2pz of one nitrogen atom, 2pz of another nitrogen atom, either above or below. Sideways overlapping takes place again. P pi and P pi is formed. P pi. One student asked in previous class, sir, what about P pi and D pi bonds? The nitrogen do not form any, nitrogen do not form your P pi and D pi. N do not form. Why it do not form? Because of absence of a d orbital in its outermost orbit. In our previous class, when student asked why sir it do not form, means this is the reason, absence of d orbital. Whereas other elements like phosphorus, arsenic, antimony, bismuth, based on their electronic configuration, here phosphorus 15 atomic number, that is 1s2, 2s2, 2p6, 3s2 and 3p3, 3d is there. In first excited state, 3s1, 3p3 and 3d1. Here 1 electron, here 3 electrons, and here 1 electron. It contains 5 degenerated orbital. Here 1, here 3 electrons, here 1 electron. So here the 1 s orbital, 3 p orbital, and 1 d orbital undergo intermixing hybridization. It gives 5 sp3d hybridization. D orbitals are also involved. That's why phosphorus onwards it forms a p pi and d pi bonds. Phosphorus also involves. How it form means d orbital also involved in phosphorus. How it involves, I'll explain. Just listen with one example. For phosphorus, here we can take one example for that. Here R3PO like this. This we can write like R3P double bond O. So R3 means alkyl group, that is CH3 taken thrice BP double bond O. This is around phosphorus here. Here 3 carbon atoms are bonded like CH3, and here the CH3, one is with the oxygen atom, one lone pair. And one more here, 1, 2, 3, 4, fifth electron is there. Here it is the fifth electron, 3d orbital of phosphorus. So the d orbital, 3d orbital of phosphorus, and p orbital, that is 2pz of oxygen. Here the sideways overlapping takes place. Lateral overlapping or sideways overlapping takes place. It forms a d pi and p pi. D orbital also involved. That's why it is a double bond. That is also called p pi and d pi bonds. Whereas in case of nitrogen, do not, because absence of absence of d orbital. Whereas in case of phosphorus and other elements, d orbital also involved and availability is there. That's why wherever or whenever required electrons are excited from lower energy level to the higher energy level, d orbitals are also involved. Like with the phosphorus, oxygen, or also we can take p double bond CH like this. And here we can take CH3 and CH3 this is. Now here around carbon for for valency unpaired electrons, tetravalency, it is bonded with 2 hydrogen atom. One is with phosphorus sigma covalent bond is formed, and one is pi covalent bond, that is p orbital of carbon and a d orbital of phosphorus. It forms a p pi and a d pi bonds. Clear about p pi and d pi? In last class, some student asked what about pi and d pi or p pi and p pi. Clear here. Just in that previous class, just one idea given about formation of bonds. Now here in anomalous properties of nitrogen, clear information given about p pi and p pi, d pi and p pi bonds. Clear? Then after these anomalous properties of nitrogen, some important chemical properties, chemical reactivities. Chemical properties are chemical reactivities. Chemical reactivities of properties of 15th group elements. In 15th group elements like nitrogen, phosphorus, arsenic, antimony, and bismuth. These are generally denoted by the symbol E. Element are also denoted by M. This is wherever or whenever like symbols are there, better use E or M for 15th or 16th or 17th or 18th group element symbol like M or E, nitrogen, phosphorus, arsenic, antimony, and bismuth. Now, first thing I'll explain in your textbook reactivity towards hydrogen given. But first, I'll explain about reactivity towards metals. Reactivity towards metals. Why are the reactivity towards metal introduced means to explain next property reactivity towards hydrogen. We want this simple concept. That's why first introduced this. Now, in this reactivity towards metal, generally element, this 15th element means their 15th group element. Element, generally it is reactivities, react with the metals in all the cases. This element shows here the -3 oxidation state. Because there are 15th group elements, common oxidation state is -3, +3 and +5 oxidation state. This is the common oxidation state of 15th group elements. In these metallic compounds, in its metallic respective compounds, your element E shows here the -3 and metal shows a variable oxidation state like +1, +2, +3 or +4 and so on. By using this, yeah, I'll take first I'll writing metallic compound. First I'll take always cation. Like I'll take calcium is a +2 oxidation state. Combines with the element E, that is always -3. So in metallic compounds, 15th group metallic compounds, that element always exhibit a -3 oxidation state. Even bismuth also generally shows only +3 oxidation state. In these metallic compounds exhibit a -3 oxidation state. By crisscross method, leave this minus and plus. Yeah, 3 is with this and 2 is with this. We'll get here Ca3E2 like compounds will get it. Now I'll take this element is nitrogen like calcium plus 2. Nitrogen nitride -3 by crisscross method will get calcium nitride CaN3 this is. If you take P-3 phosphide, as I explained, trinitrides like N-3 is easily formed, but P-3 is not easily formed because size increases, electronegativity decreases. React with the same calcium by this method, here we'll get Ca3P2, this is calcium phosphide. Same here, instead of that, take here the sodium +1, here the As -3 by crisscross method, here we'll get Na3As, sodium azide, arsenide. Now here the zinc +2 and here the Sb -3. Sir, both are metals. How it shows means based on their electronegativities. Here high electro means electropositive character, less electro means negative nature. By crisscross method, we'll get here Zn3Sb2. This is zinc stibnite. Like magnesium Mg +2 react with Bi -3. By this method, we'll get Mg3Bi2. This is magnesium bismuthide. So these are the some important metallic compounds of 15th group elements. In reactivity of 15th group elements, reactivity towards metals. In all metallic compounds, yeah, 15th group elements always shows here the -3 oxidation state. Metals variates. That is the main important key role for objective or any other commutative examination. Then next thing is very important concept is second one is reactivity towards hydrogen. Towards dihydrogen H2. Generally, industrially, to prepare this respective hydrides, 15th group hydrides. Your 15th group hydrides elements we know A is equals to nitrogen, phosphorus, arsenic, antimony and bismuth we know. Reacts with the hydrogen, it forms a corresponding hydrides. These are the corresponding hydrides. It forms like EH3 type hydrides. So the EH3 type hydrides are formed. So commercially, industrially, to prepare this hydrides, 15th group hydrides, we can use these metallic compounds of 15th group elements. So are the metallic compounds of 15th group elements like Mg3N2 or Ca3P2 or your Mg3As2 like Zn3Sb2 or your Mg3Bi2. These metallic compounds react with dilute water or acidified water in acidic medium and gives corresponding hydrides. For this purpose, to explain this point, reactivity towards metal explained to you. Now, a formation of this metallic compound, these metallic compounds are treated with water or acidified water, it gives corresponding hydrides. Now, the magnesium combines with these are, for simple example, magnesium nitride combines with water in acidic medium, then it forms magnesium oxide MgO plus your NH3, one type of hydride of 15th group element is formed. Now, balance this here, take 2 moles, 6 water molecules required, that's why take care of the 2 moles, it is balanced. And take care of the 3 moles of magnesium oxide and 2 moles of ammonia gas is liberated. Similarly, in this manner, by using all these metallic compounds of 15th group elements reacted with water, we will get the corresponding hydrides of 15th group elements. Here NH3, one hydride, PH3, ASH3, SBH3, BAH3, all are the some important hydrides of 15th group elements. Or some cases directly your element of 15th group element directly react with the hydrogen gas, pure and dry hydrogen gas, it gives corresponding EH3 like. The 2 moles, take care the 2 moles and 3 like will get it, 6 balanced. Direct combination of metallic compounds means 15th group elements and hydrogen will get the corresponding hydrides. Anyhow, your 15th group elements, 15th group elements like nitrogen, phosphorus, arsenic, antimony do not form, very, very important, do not form EH5 type hydrides. Why? Reasoning question. Your NH5 do not, always do not form. The pH5 possibility is there to form, but not possible because of a reason for this, because of small size, very small size of hydrogen. This is a very, very important reason. That's why 15th group elements forms only EH3 type hydrides only. So the EH3 type hydrides, by using all 15th group elements, once we can observe your hydrides of 15th group elements type is EH3, that is NH3, the PH3, ASH3, SBH3 and BIH3, these are some important hydrides. Now, based on this guarantee, we can expect one question either in a PUC or in objective or any competitive examination. Increasing or decreasing orders of their corresponding properties of hydrides of 15th group elements. Clear? So here in 15th group elements, hydrides like first one is NH3, that is hydrides of nitrogen, hydrides of N. In this hydrides of nitrogen N, one is NH3 ammonia, this is, its name is ammonia, And also one more is there, that is N2H4 is there, that is called hydrazine. And also N3H is there, that is hydrazoic acid. That hydrazoic acid is monobasic acid. Here in this monobasic acid, basicity is equals to 1. Acidity of that base is equals to 1. Monobasic acid. Now these are the three important hydrides of nitrogen. Here ammonia, in this ammonia around nitrogen, 5 valency electrons are there. Among 5, one is a lone pair, remaining 3 are the bond pairs like this. This is ammonia. Now hydrazine is N bond N like this. Now here the H and here the H, and here also hydrogen and hydrogen. Here one lone pair and here one lone pair. Like N3H is there. Here one is like double bond N bond H. Like here one lone pair, one is coordinate bond. Like N3, one more is there. Like N triple bond N, here the single bond here, double bond N, single bond H. Yeah, each and everyone containing one lone pair like this. So here in this case, nitrogen oxidation state here the +1, +1, +1, composite is -3 oxidation state. Now here +1, +1, here +1, here +1, composite oxidation state is minus each oxidation state, here -2, here -2. Now as to explain about N3H, here the 3x we don't know, +1 is equals to 0, 3x is equals to -1, x is equals to -1/3, oxidation state of here. Each and every one element ratio, 3 nitrogen atoms are there, only 1 nitrogen atom is there, each nitrogen atom oxidation state ratio is -1/3. Ammonia, hydrazine. In organic chemistry, most important formula this is. In aldehydes, ketones and carboxylic acids, reaction with hydrazine of aldehydes are the ketones. Condensation reaction takes place. Ammonia and its derivatives properties are there. Next, after these hydrides of nitrogen, hydrides of phosphorus. Are the two important hydrides are there. Phosphorus, general two important hydrides. One is phosphine. Hydrides of P, this is. That is PH3, that is phosphine. Now another one is here the P2H4, that is diphosphine. This diphosphine is generally least stable hydride it is. Remaining elements hydrides. Hydrides of arsenic, antimony and bismuth common, that is AsH3, SbH3 and BiH3, these are. This is a story about hydrides of 15th group elements. Different hydrides of 15th group elements. Okay, we know there are some important hydrides, common hydrides of 15th group elements. That is one is ammonia, phosphine, arsine, stibine, bismuthine. This is ammonia. We know regularly we can use this ammonia. This is phosphine. Phosphine method is there, a preparation method I will explain. This is arsine, this is stibine, this is bismuthine, this is. Based on all this, some important properties are there for objective as well as theory. Here EH3 is nothing but hydrides of 15th group elements. Central atom of an element is E element. Around the central atom of an element, 3 sigma covalent bonds are there and one is lone pair is there. So it is LP and these are the 3 are the bond pairs. That's why central atom of an element undergo sp3 hybridization. Because they are the hybridized orbitals are number of for this neutral molecule, number of lone pairs plus number of bond pairs. Now here the lone pair is 1, bond pairs are here 3, 4 pairs are there, one is a S and remaining 3 are the p orbital. That's why sp3. Generally, according to hybridization, if it is sp3, molecule is tetrahedral. But after hybridization concept, after VB theory and Vesper theory in chemical bonding, there is one important concept, lone pair, repulsions are more than compared to the lone pair, bond pair than compared to the bond pairs and bond pairs. So due to the occurrence of lone pair and bond pair repulsive force, second one here, its geometry is not tetrahedral, changes to a pyramidal structure, pyramidal geometry. Here geometry is tetrahedral, its bond angle is originally 109 degrees 28 minutes, but its bond angle also reduced from 109 to a 107 degrees. Reason is repulsive forces, compression like repulsions increase, bond angle decreases. So in all the 5 cases, 5 examples, geometry is same, pyramidal, but bond angle changes. Now here the first one is some important points. First one is about bond angle. So the bond angle is NH3 is greater than compared to the PH3, than ASH3, than SBH3, than BIH3. Reason behind that, why bond angle here 107 degrees, here 90 degrees, why are the bond angle decrease from nitrogen to the bismuth means, very important reason, here central atom of an element changes, nitrogen, phosphorus, arsenic, antimony and bismuth. So whenever central atom of an element changes, atomic size what happens? Increases. Atomic size increases, repulsive forces decrease. When our repulsive forces decreases, bond angles also decreases. That's why your bond angle is NH3 is greater than compared to phosphine, compared to all the remaining these 3. But geometry is same, pyramidal structure. So whenever bond angle decreases, repulsive forces decrease, polarity also decreases. Polarity, we know dipole moment and polarity, mu is equals to E into D. Polarity also decreases. When our polarity decreases, solubility also decreases. Solubility of the hydrides and polarity of the hydrides, all they are the same order. So whenever size increases, generally according to the Lewis acid-base theory, electron pair donor is a Lewis base, electron pair acceptor is a Lewis acid. Now all the hydrides are generally on a central element, on each and every one hydride of 15th group element on each central element, like EH3, one lone pair is there like this, one lone pair. So this lone pair is ready to donate to the other group of elements or the group of metal ions or the any species. So the electron pair donor is a Lewis base. This Lewis base also acts as a nucleophile, also acts as a ligand. So for nitrogen, polarity is more than compared to phosphorus, than compared to arsenic, antimony and bismuth. That's why donation capacity also increases. That's why basic strength also increases. That's why very important concept is after this, bond angle, solubility and polarity are the basic strength. Are the basic strength of hydrides, that is NH3 ammonia is more than compared to PH3, than compared to ASH3, SBH3 and BIH3. This is basic strength, polarity, solubility, bond angle, and also bond energy, bond enthalpy also same. For all the 5 or the 6 important characteristics, same order. Which of the following is the correct order, increasing order, decreasing order of hydrides of 15th group elements? They'll ask like. Okay. So after this, based on this basic strength and polarity, bond enthalpies and solubility and bond angles, central atom of an element here, nitrogen, phosphorus, antimony and bismuth size increases, your bonds strength decreases, ready to produce H plus ions. When are ready to produce H plus ion, the removal of hydrogen is called a oxidation. In oxidation process, participated molecule acts as a reducing agent. That's why reducing nature very, very important. So the reducing nature of hydrides of 15th group elements is NH3 is less than, PH3 is less than, ASH3 is less than, SBH3 is less than BIH3. This is the strongest reducing agent. This is the least reducing agent. Least RA is the strongest reducing agent. Reason for that? What is the reason? Because of bond length increases, bond strength decreases. Then ready to produce H plus ion, removal of electrons easily takes place. Oxidation reaction takes place. That's why BaH3 acts as the strongest reducing agent. Clear? After reducing agent, once we can observe ionic nature. In ionic nature, once we can observe here the electronegativity difference is less, but here in BaH3 electronegativity difference is more than 1.7, that is ionic in nature. So by using simple explanation, simple point, electronegativity is same order, ionic character also same ionic nature. NH3 is least ionic than compared to PH3, then ASH3, then SBH3, then BIH3. This is ionic nature, reducing nature. Clear? So bond angle, solubility, polarity, basic strength of bond enthalpies, reducing nature and ionic nature. One more important point is here enthalpy of formation of hydrides. Bond enthalpy is different, bond energy is different, bond enthalpy of formation. So the bond enthalpy of formation, see it, or bond enthalpy of formation. Bond enthalpy of formation means standard conditions means H naught F. This is of hydrides of 15th group elements. Now here NH3 is less than more because while forming here the negative value produces, amount of it is liberated. Then PH3, then ASH3, then SBH3, then BIH3. Enthalpy of formation of BIH3 is greater than compared to NH3. So the reducing nature, ionic nature, and its bond enthalpy of formation of hydrides. So 15th group also same. Yeah, remaining last thing is points, boiling point and melting point. Observe carefully. So here generally NH3, your PH3, ASH3 and SBH3 are the BIH3 among these. So in general case, general condition, yeah, the top to bottom are same hydrogen, but central element changes. Nitrogen, phosphorus, arsenic, antimony, bismuth, atomic number, atomic mass increases. Their temperature values, either boiling or melting points, increases. Whereas in case of this particularly, nitrogen position is here. This is because between ammonia molecule and ammonia molecule, there exists one type of bond. Between ammonia and ammonia molecule, there exists one type of bond. What is that? In first year chemical bonding explained. There is a hydrogen bond that is between highly electronegativity fluorine, oxygen, nitrogen, and between hydrogen there exists one bond that is called a hydrogen bond. There are two types. There are intermolecular hydrogen bond as well as intramolecular hydrogen bonds. Only the hydrogen bond is exist between hydrogen fluorine, hydrogen oxygen, hydrogen nitrogen. Here nitrogen is there, but there is no phosphorus, arsenic, antimony, and bismuth. That's why between ammonia and ammonia molecule, there exists a intermolecular hydrogen bonds. Due to the presence of intermolecular hydrogen bond strength is more between molecule. Attractive forces are more. To vaporize this, more temperature required than compared to the phosphine arsine. That's why correct order is boiling point pH3 is less than, ASH3 is less than, NH3 is less than SBH3. Now here this is the metallic compounds. This is the boiling point region, and your melting point also same. That is pH3 is less than, ASH3 is less than, SBH3. Better you write lastly in melting point NH3. This is very, very important point. Okay. About reactivity towards hydrogen for objective as well as subjective, for commutative as well as theory. If they ask any question, better you follow these notes or any NCERT material. Guarantee will get one or two questions, reasoning questions based on this. Reactivity towards metals, reactivity towards hydrogen completed. The next one is reactivity towards oxygen. Reactivity towards oxygen or the dioxygen O2. This is. We know element, this is 15th group elements, nitrogen, phosphorus, arsenic, antimony, and bismuth. Generally, this 15th group elements forms two types of oxides. Two types of oxides. They are, one is E2O3 type, another one is E2O5 type. So here, if you can create one table, here are some important oxides. Here are some important oxides of this. First one is N2O3. This is N2O5. Now here the P2O3. Here N2, P2O5. This is AS2O3. Here AS2O5. Now here Sb2O3. Here Sb2O5. Bi2O3. Bi2O5. These are the some important oxides of different types of oxides of 15th group elements. Now once we can observe here, in this case, oxygen is -2 always. Here also oxide is -2. Now here the nitrogen, once we can observe here, oxidation state is +5 oxidation state. Now here +3 oxidation state. In all the cases, here phosphorus is +3, here +3, here +3, here +3. Your oxidation state is +5, +5, +5, +5 and +5. Once we can observe here, one important thing is Bi2O5. In Bi2O5, generally here +5 oxidation state. Bismuth do not shows or do not exhibit generally +5 oxidation state. Why? Why do not exhibit +5 oxidation state? Because of its inert pair effect. So in bismuth, in its outermost orbit, like a rare gas NS2 and NP3, inner electrons d and f orbital, electrons directly influences on its outermost orbit, drag it towards nucleus. These NS electrons do not involve in chemical bonding. That's why only +3 common oxidation state and stable. That's why it is unstable. If it is forms, it is generally not stable. Unstable cannot exist. Ba2O5. Because bismuth is generally exhibit +3 oxidation state. Clear that side. Next. One important thing is common important point is generally in all oxides like E2O3 and E2O5, higher oxidation state. Higher oxidation state oxides are generally more acidic in nature. More acidic in nature. So by using all these type of oxides, which is more acidic oxide? N2O3 to Bi2O3, N2O5 to Bi2O5, which is most strongest acidic in nature oxide? N2O5. Sorry, here +3, +3, +3, +3, all are +3. Here all are +5. Sir, all are +5 oxidation state na? Highest oxidation state na? So all are most acidic. Comparing these all 5, your N2O5 is the most highest acidic in nature. This is all among all E2O3 and E2O5. Strongest means more acidic nature compound is N2O5. By using this, your acidic nature of oxides like E2O3 is like N2O3 is greater. Here the P2O3 is greater. Here AS2O3 is greater than Sb2O3 greater than Ba2O3. Now here the E2O5, same situation, N2O5 greater. Here the P2O5, then AS2O5, then Sb2O5, then Bi2O5. By using this, your atomic size and electronegativity, based on electronegativity and atomic size, electronegativity is more, atomic size is less, means small atomic size, more electronegativity, that is more acidic in nature. That's why these two are generally acidic in nature. Generally, these are amphoteric. What is the meaning of amphoteric? Acts as both acidic as well as basic in nature. Means reacts with, it can react with both acids as well as bases. Now, this is basic nature. That's why, yeah, the acidic strength of trioxides and pentoxides. Clear the story about oxides of 15th group elements, two different types. So, table created, very, very important table. This is based on this, we can easy to say, easy to answer for any objective like oxides, acidic, basic, which is more basic, which is less basic, more acidic, least amphoteric, +5, +3 oxidation state oxides. Then here are different types of oxides of nitrogen are there. I will explain later. That is N2O3, N2O, NO, N2O3, like N2O4, N2O5. Story is there. Tomorrow I'll continue. I'll explain some important oxides of nitrogen. Nitrogen again forms some different important oxides and shows variable oxidation states. Here +1, +2, +3, +4 and +5 oxidation states. Tomorrow I'll continue. Tomorrow I'll explain. Before that, one important concept is there. There another third important, fourth important property is reactivity towards halogens. What are halogens? 17th group elements are halogens. Are 17th group elements denoted by X in terms of atomic state. Fluorine, chlorine, bromine, iodine, astatine also present. It is a solid metallic radioactivity nature. Molecular state X2, that is F2, Cl2, Br2 and I2. This is. So reactivity towards halogens. Your 15th group elements are nitrogen, phosphorus, arsenic, antimony and bismuth. So directly these elements react with halogens. It forms EX3 type, as well as reacts with reacts with X2. It forms AX5 type. Means two different types of halides are formed. Now the element is here AX3 type. Like element by using N, we can use X is, I'll take here Cl, NCl3, here the PCl3, here AsCl3, here SbCl3, BiCl3. This is here X is chlorine. Then here EX5, if you can take chlorine, here NCl5 do not. Why? Reason I will explain. Do not. Now here the PCl5, this is AsCl5, like SbCl5, like. So these are the some important halides. If you can take chlorine related chlorides, will get it, like related chlorides. Yeah, one of the most important question is here NCl3 is possible, but NCl5 is not possible. Why? Give reason. So these are generally trihalides. These are called trihalides. This is a pentahalide. The nitrogen forms, N forms only trihalides. trihalides but not pentahalides. Why? But not pentahalide. Why give reason? Only one, that is answer is here due to the absence of d orbital in its outermost orbit. Electrons cannot excite from lower energy level to the higher energy level. Now here the nitrogen we know, Lewis dot method, number of valence electrons are 5, lone pair it is. Here the 3 are the unpaired. Chlorine we know, Lewis dot method, 7 valence electrons are there in its outermost orbit. This is a Lewis dot structure for chlorine. So each chlorine contains one unpaired electron which is bonded with mutual contribution, mutual sharing takes place. It forms one covalent bond. It forms one more covalent bond. Now it is one lone pair. Now the same thing is here. 3 sigma bonds are there. 3 sigma bonds and 1 lone pair. Number of hybrid orbitals are 4. That's why it undergoes generally sp3. Even though sp3 do not undergo tetrahedral, its geometry is pyramidal geometry, trigonal pyramidal geometry, trihalides. These trihalides undergoes generally sp3 are trigonal pyramidal structure, whereas in case of pentahalides like nitrogen, here are 5 bonds required, okay, 3 Cl bonds, and 2 more bonds required like Cl and Cl. These 2 electrons cannot excite due to the absence of d orbitals. That's why here the nitrogen do not forms any pentahalides, only trihalides only, whereas the other phosphorus trichloride, phosphorus pentachloride. So here phosphorus, here the 5 valence electrons are there. Here 1 electron exit from 3s2 to 3d. That's why here 5 unpaired electrons are there. With this chlorine, 5 chlorine atoms are bonded like 5 chlorine atoms. Now this phosphorus contain 5 sigma covalent bonds. That's why 1 s orbital, 3 p orbital and 1 d orbital is there. Total 1 plus 3 plus 1, 5 are there. It is sp3d, that is a bipyramidal, trigonal bipyramidal structure. Bipyramidal structure is there. There in phosphorus compounds, one of the most important question based on PCl5, there I will explain very clearly. So generally trihalides undergoes sp3 and pyramidal, it is bipyramidal, trigonal bipyramidal structure. Why nitrogen do not form pentahalides? Reason is that. Okay, so tomorrow I'll continue continuity part based on these reactivities. Preparation methods are there. Preparation methods of some simple dimeric compounds like dinitrogen and hydrides of nitrogen, NH3 ammonia, and oxides of nitrogen and its corresponding molecular Lewis dot structures, and oxo acids of nitrogen, nitric acid. Tomorrow I will complete maximum about a nitrogen story. Okay, thank you.